We'll be okay. As was said before, I'm Dr. Moser, and I see many of my music students that I recognize, and I hope, I'm brand new here, this is my first year, so I hope to start to recognize the math students. I was a math student, I would have been on the math table when I was in undergrad, not with these musicians, and I turned out to be over on the music side too. But as you'll see from today, it's okay, you can mix the two, it's great. My title is very intentionally wordy. I mean, I guess it's only 2 words, but syllabically it's a little large. Enumerating indeterminacy. I think we know what enumerating means, counting. The indeterminacy part, well, let's talk about that. What is this? Let's let 2 people that are very important to me and important to music say it first, and I'll do my very best to explain what they mean. First of all, this Frenchman, Pierre Boulez. Why compose works destined to be renewed at each performance? A development that is fixed in a final way has struck me as no longer coinciding exactly with the current state of musical thought. Or, Mr. John Cage, my favorite by far, the function of a performer of this type of music, this indeterminate music, is comparable to that of someone filling in color where outlines are given. There was this push, as you hear in Pierre Boulez, due to cultural changes. There was this push in the 50s and 60s to step out of your normal, average, everyday forms of music and give control, give the keys in the car to the performer, and let the performer decide what the piece actually becomes. And I don't mean jazz and improv. What I mean is more like a book. I don't know if any of you students read Choose Your Own Adventure books, but more like that, where you have a book, and in the book, you read a page, and after that page, it says something like, well, if you would like to go into the haunted house, turn to page 6. But if you don't want to go into the haunted house because you're a coward, turn to page 20 or something. And you have then the option of making the story whatever it is that you want. You would still say that that's kind of like one book, right? But then how many stories are in that book is a question that is worth asking. That's a little bit like this music. This music is one piece of music, but how many different ways can we get from the beginning to the end is up to the performer. And that was something that interests me a lot. Here, I'm going to show us some examples here. So don't be freaked out. I'm not going to play any of these. I won't ask you to play them. A lot of them don't even look like music at all, like this one. For those who have been to my office, I have this piece, and it's 76 friends on my wall. This is one of my favorite pieces to look at. It actually was shown as visual art before it was played. But as you can see, there are lots of options in this for the performer. I don't have to play everything, for instance, in the instructions that John Cage gives. You don't have to play everything. You can play nothing if you want. We could play this piece right now. Done. Why did even some of the notation is totally up to you. I won't go into the details of all of these notations, but he invents notations that are up to you. As you can see, this is very free, right? Very open-ended. Even more open-ended. Earl Brown, one of John Cage's disciples. Anyone want to play this? How lovely, right? Performances of this range from, you can get recordings of this and you would never know that you were hearing the same piece. Some people consider, I don't know, maybe this playing, or maybe this direction is pitch. Maybe this direction is timbre or time. I don't know. Maybe you just want to turn it around. Maybe I'm showing it wrong. You can see his name is written that way, so he wants it this way. But maybe pitch is this way. I don't know. Whatever you want to do. Oh, yeah, good. Go for it. You can imagine every piece that would be performed like this, every realization of this would sound different, right? A little less open-ended is this. This is for violin and piano. Have a little duet. P means pizzicato, A means arco, so pizzicato means we're plucking our strings, arco means we're using our bow. This is a harmonic. This just means play a low pitch, play a high pitch, play a medium pitch, doesn't matter which one. So he's giving a little bit of control to us performers, but not total control. He doesn't want here a high pitch, for instance. He wants a low one. He's kind of honing in on what he wants. This is for piano. 3 sounds in the high register, 1 in the low. These little bars this way are actual measures, if you think of it. So if we decide that this is how long that each one of these boxes goes. Yeah. So it progresses that way. It's Mr. Morton Feldman. we'll talk more about him later. And again, for Mr. Boulez, this is exactly a choose your own adventure. At the end of these, we have symbols. These symbols, we can go to any one of the symbols that has this little symbol. And so some of the red ones, I don't have one that's actually in red, but I have to go from green to red to green. And so somewhere there's red ones that have this symbol at the beginning of it. So I can go to that one if I want, or I can go to another one. This piece is very long, very difficult to play as you can see if you are a pianist. Sounds like someone banging on a piano. I'd say that lovingly. I'm a pianist. Karl-Heinz Stockhausen, another of the fellows that we're going to look at today. This is for percussion, and it is a score that is a circle. And you may start anywhere, and the percussion instruments are where the score is telling you to play those percussion instruments. And so right here are where the tam-tam music is, and then here's where the cymbal music is, and you go around like this. And you can turn around and go this way if you want, and so forth. Very indeterminate. And then last but not least, not music, but something that will help maybe us to visualize something that we're about to have to talk about. This is Alexander Calder, a sculptor, American sculptor. And this, as you can see in his red petals, this is a mobile. You guys probably, if you don't remember when you were children, you had mobiles, but you've probably seen someone else's kid with a mobile in which things are turning. And so this form, right now where I took the picture, snap, yeah, that's one form, but I mean, if even just the tiniest bit of gust of wind or something hit this, it's never going to be in that form again. Y'all agree? It's never going to look like that again. All right, big question for the day. How open-ended are these pieces that we look at? How much control was given to the performer and how little control? Are these infinite or are they countable? Well, we looked at some that I would argue probably are on the more infinite side, like the red petals. Think about how many configurations you could put those red petals in on that mobile. I mean, there's no way to count that, right? The gradations of these little petals, these little movements, that's all on a spectrum that's a continuous spectrum, and there's just no way to actually count that. But Mr. Boulez and some of the other guys, this was the choose your own adventure, you could probably count that. Yeah, it might be a big number, but you could probably count it. It's probably not as many. Just for historical purposes, most of the time, it's the Americans that don't care one bit about the amount of the control that they give. They just say, hey, you do whatever, I don't care. And it's the Europeans that are more like, no, you do what I tell you to do. We, in music history, I know this is a math lecture, but in music history we've talked a little bit about this. I think, my theory is that coming out of World War II, which happened mostly, of course, in the grounds of Europe, not only there, most of the composers were very into controlling their music tightly because they had lost control for the last 10 or 20 years, and now it's time to grab the reins again. But that's more history than it is math. Cool. Sometimes the performance directions that the composer gives only permit something that's finite, countable. And before you freak out, what I mean is that the actual directions produce finite, not the number of performances. If you tried to count the number of performances of any piece, even the smallest little piece of music, well, you could argue that you never can play the same note on a trumpet twice, or you never can play the same note exactly on a violin twice, or a piano. The dynamics are gradations of a continuous spectrum. You can't count that. So I have to disregard all of this. And so for this lecture, we're disregarding all of the nice things about music, like timbre and tempo and attack. And we're only counting directions. We're only counting orderings of events. All right? So we're disregarding all of this, and we're only looking at the order of events. And so as an example, Mr. Beethoven, I've probably heard, I don't know, there's probably 50 recordings of the Ninth Symphony on my laptop. It's a big piece of music, and I like singing, I like to hear the choir. How many different orderings of events, though, does Beethoven permit in his Ninth Symphony? How many options do you have at some point to either go somewhere else and skip this part, or I don't want to play these notes, I'm skipping these measures, or I'm going to go and play these measures again? There's only one. He only gives us one option. Yeah? Mr. Stockhausen, though, in one of the pieces that we're going to look at, He gives us a couple more options, so we're going to have to count them. So here's our goal. Here's what we're going after. We're going to look at two pieces. One of them is a European, one of an American. Klavierstück 11 is a very famous piece by Stockhausen. And the Durations 2 is not one of Feldman's most famous pieces, but it is a piece that is famous because of the group of pieces it is in. Anyway, we are going to look at their instructions, and we're going to mathematically model them so that we can count how many stories are in the book, how many realizations are in this piece, okay? How many different orderings of events can we come up with? Y'all with me? Early enough to answer? We're not going to answer out loud? Okay, so we got to warm up, and we got to warm up quickly because we've already gone 10 minutes. Ready? Do you have your math genius heads on? Let's go. Warm up. Raymond Queneau, 100 milliards de points. 10 sonnets. Of course, this isn't music, but we got to warm up. 10 sonnets, 14 lines. You know sonnets, right? A, B, C, D, C, D. You all know your English? All right, well, we're French for this matter. Anyway, this is, of course, the English version. 10 sonnets. Each line has 10 behind it, right? Or 9 behind it. And I can choose any first line I want, and any second line that I want, and any third line I want, right? So how many options do I have for my first line? 10. How many for my second line? 10, and so on. 10, 10, 10, 10, all the way. 10 times 10 times 10 times 10 times 10 times 10. How many? 14 lines, right? So this many. In this book, there are that many poems. 10 to the 14. Let's see. Does anyone know French? 100? 100? Milli? 100,000? Milliard? Billion. Or 10 to the 14th. Cool? Big number. That was easy. Warm up 1. Warm up 2. Earl Brown, an American cage disciple. 25 pages for 1 to 25 pianos in 53. All of this music and stuff is going to be 50s and 60s. This was just like a hot time for us. It was hot right now. All right, 25 pages played in any order. That's different. And also, either right side up or upside down. But you magicians out there, that shouldn't scare you, right? So let's pick the first first page. How many choices do we have for the first page? 25. But after we pick the first page, when we're picking the second page, we don't have 25 anymore, right? We have 24. And then for the third page, we only have 23. And for the fourth, and then we have 22 and then 21. So how do we model that mathematically? You all know that. Factorial? Yeah? 25 factorial. And the only difference now is that each of them, but wait, there's more. Each page can be played one of two ways, right side up and upside down. So how many ways can you play the first page? 2. How about the second page? 2. Third, 2, 2, 2, 2, 2, 2, all the way 25 times, right? 2 to the 25th. Therefore, you multiply these things together and you get this many ways of playing. Oh, keep your shirts on. It's way bigger than this. So, what is this? Let's see, 5, 10, 15, 20, 25, 30, 33 digits long. Part of the difficulty of lecturing like this with these big numbers is that this is just so big you can't understand it, right? So I have to try to make interesting, fun ways of thinking, well, how big is that stupid thing, right? Well, I'm not going to ever name any of the numbers from now on because the names get too long. It would take me an hour to name some, to actually physically read some of the names. This one starts with nonillion, octillion, septillion. These are illions that we don't really talk about much anymore, although they exist. Yeah. All right, so let's have this on our bank account. Okay. Let's go to the ATM and let's take it out. I want it in cash. Getting it in ones would be a little silly. So let's get it in billion-dollar bills. Is that okay? Let's get it in billions. So the ATM starts going boom, 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 boom with billion-dollar bills. How big is the stack? Yeah? Bigger? Bigger? Okay. The stack can go all the way to Pluto and back 1,000,000 times. Okay, so we're going all the way to Pluto and back, and we do that 1,000,000 more times, and that's our money. Yeah, we can carry it to the bank. Yeah. These are absurd. These numbers are absurdly big. But it's exactly that, right? It's not one more or one less than that. That's what I like about this. That is an exact number. It's not just like saying it's big. No, it's exactly that number. All right. That should be it. Warm-up examples, we're 15 minutes in, we gotta go. Mallarmé, this one doesn't have a date because we didn't finish it. Last example, then we'll do music examples. And this is the hardest example. Follow along, you can be fine. Okay, so this is just pages that he wrote, and he wanted you to read any of them in any order, and you didn't have to read them all. You notice the difference now? Not having to read it all, read them all, changes things. Okay. Also, we don't know how many pages he wrote, so we have to use X. Oh, now we're really in the math now. We're using a variable. All right. All right. So, from Earl Brown, if we're going to read them all, how many different ways can we do it? We're going to read all X pages. X factorial. Yeah, that's easy, right? That's if we're going to read them all. We know that. That's easy. But what if we want to read one page only? Or what if we only want to read 2 pages? Or what if we only want to read 3 pages? And so on. We have to count those too. Those count. Yeah, those count. So, how many different ways are there to read only 1 page? How many different pages are there? X. How about 2 pages? First, pick the first page, X. Then pick the next page. X minus 1. Third, X minus 1, X minus 2, yes. And then so far, all the way down to however big X is, X realizations, X factorial. Now, we have to somehow, we're getting our picture taken. We have to somehow count all of these up. Now, don't freak out, you music people, but math people shouldn't feel like this is anything hard, right? Let's make a dummy variable, n, and let's run n through 1 to x, yeah? And let's just count all this up. Let's not take too much time to explain this, but this is the same as counting up all of these. Math people will follow easy, music people, you got it, I think. I trust you. So, let's just assume how many pages is a decent number of pages for a very famous poet to have written. I thought 50 for this morning would be just fine. So let's just imagine he had written 50 pages in his book. That's how many ways we can read 50 pages. Exactly that, not one more or one less. Just interesting. What is this? 10, 20, 30, 40, 50, 60, 65 digits. I looked up this morning that the number of atoms in the universe is often counted somewhere between 70 and 75 digits. So this is almost as many atoms in there as there are in the entire universe. Just with 50 pages. Cool. That's why the atoms in the universe shows up. All right, so are we cool with our tools? Factorial, we know. Summation notation, we know. Okay, I have to add 2 more, but these aren't going to be hard for us to do. Y'all know product notation? You math people, of course, will. This is the same as summation, but this is when we multiply numbers together. We're going to need that. And then, last but not least, one that I cannot take as much time as I'd like to explain, but
combination.
A concise way of using combination notation. Just like this, choose this. 52, choose 5. How many different ways can you choose 5 cards from 52? Well, this be that many ways. Right? That's what that means. Don't worry about how it's derived or whatnot. Right? You math people won't know that. I'm sure you use combination notation, right? Okay. Okay. We're 15 or 18 in. Now we have 2 heavy hitters, our big ones. I mean, not too big. Maybe we used examples that would resonate in this crowd, but I think we can follow along just fine with these. Here's Morton Feldman, one of my favorite guys. And the piece is so simple. The directions are so simple. He says, play with free duration. That's all he says. Easy. Easy. We got a cello part and a piano part. The cello part has 50 sounds to be made, and the piano part has 49 sounds to be made. That's it. And so I asked, when I was a little older than you, I asked, how many ways could we play this? How many different pieces are really here? You understand what I mean, right? Like, maybe the cello wants to go first and then the piano. Maybe the cello wants to play up to here before the piano even comes in. Maybe the piano plays his entire entire piece, and then the cello plays its entire, or her or his. We can even play at the same time, too. That's something that's interesting. All right, let's model. Okay, so easiest way to do this is how I did it. And I think part of the reason I wanted to make this lecture how I've made it, with kind of like the fill-in-the-blank stuff, is that I only had a math degree when I was doing this stuff. It was just undergrad, so it's not like this isn't tough math. And what it is you may see a way that I did this that you're like, God, why did you do it that way? This is so much easier if you had done it this way. And you're probably right, because this is just me exploring a question. I didn't know how to answer it, so I'm just exploring. And this is my method of exploring that got me to the right answer. Maybe it was the long way, maybe it was the short way. But you math students out there, all roads lead to Rome. I mean, if you can get there however you can get there with what you know. So this is the first thing I thought. I thought, well, let's just start really basic. Let's say there's one cello sonority and one piano sonority. How many different ways could you do that? Well, the piano could go first, and then the cello. They could go at the same time, or it could go after, right? There isn't any other option, that's 3. What if there were 2 sonorities, and you had to play one? It could go before them both, it could go with the first one, it could go in the middle of them, it could go with the second one, and it could go after it. Y'all with me? That would be 5. What do you think 3 is? If I did this? 7, yes. 1, 2, 3, 4, 5, 6, 7, and so on. Yeah, that's cool. Good, I got that one down. That was easy. Let's go to the next ones. What if I'm flipping them upside down and I actually want one up here and I'm trying to do 2 down here? Well, I could do 2 before. I could do 1 before, 1 after. 1 before, this, that. You should have seen my paperwork when I was doing all this stuff, because I would just have pages and pages and pages that look like this. Dots, right? But does this make sense to you what this is? I mean, there's the one sonority, and here are the 5 different ways of ordering my sounds. And so on, 2, 2. I'm not going to do that one, but I'll just fill in the rest for you. Trust me, there they are. I went way, way higher, as you can see in this next one. This is as far as I went. I had one page that had 321, and I counted it, and I recounted it, and I recounted it, and I made sure it was 321. Going 4 sonorities with 4 sonorities. You can do it 321 ways. So I stopped here, and I say, okay, I don't want to do any more. Let's try to find a pattern. That's a math thing, right? Let's try to find a pattern. The pattern, I'm sorry to say, didn't pop out at me immediately. I don't think it normally does. This is what I thought to do. I thought I could totally model this row, right? Ones. How about this row? I can model this. What is this? It's a line, yeah? It's a real nice, easy, basic line. How about this? What's this? How do I model that? Well, that doesn't look like a line, does it? But it turns out, after some experimenting, that it's a quadratic. This one is a cubic. This one, which I couldn't get, I don't think I could get to the 4th. I might have been able to, I forget. I don't think I could get to the 4th. I think my calculator at that time couldn't do it. The furthest one I got is modeling this one. I did get the cubic. So I stopped there and I said, okay, well, this is not going to work, because if I have to go all the way, remember the piece has 50 for one of them and 49 for the other. And there's just no way I'm going to be able to model, figure out with my little calculator, you know, something that has an x to the 50th, and then an x to the 49th, and an x to the 40th. There's just no way I was going to be able to do that. So I need to think of something else. But something popped into my head when I did this. And what popped into my head was Pascal's triangle. Do y'all remember Pascal's triangle from back in the day? I remember Pascal's triangle being a line here, a quadratic here, a cubic here, and so forth, all the way down. I remember a teacher in middle school told me that. Of course, the way Pascal's triangle works is pretty easy. You just add both of the numbers right above it, and it comes out to that. So it's easy to formulate Pascal's triangle, but there's so much information in Pascal's triangle. There's combinations are in there, and like I just said, you can have, you know, a line and then a quadratic. So this is just like Pascal's triangle, and I thought, well, maybe my numbers have something to do with Pascal's triangle. So I put my numbers in a triangle. Why not? And I try to add them up, and they don't work. Don't. Of course they don't. Does anyone see how they do work? Wait for it. Boom. All you need is to add the one directly above it from 2 lines. And turns out, when I finally did this and I start Googling Pascal's triangle-like things, Mr. Henri Delanoy in 1889 had already discovered my numbers. He discovered them using tiles. He was playing with tiles. I was playing with music. We were playing with the same thing. And he already, thankfully, so I'm angry that he gets the credit. I'm not angry that he came up with an awesome formula that I didn't have to come up with. Yeah. And there it is. There's my formula. I got to it via learning about Pascal's triangle, figuring out that my numbers had a lot to do with Pascal's triangle, except not just adding those, adding this, and then Googling as many people that played with Pascal's triangle-like things as possible and finding one. It's not hard, right? Have faith, you math people. You don't have to have a lot of knowledge, you just have to add. And then find someone else who's smarter than you who already did it, and you have it right there. All right, so now when I have my formula that describes every number in this whole, as far as I want to go, and I have a strong calculator that can do it, I just have to put in 50 and 49, right? And there's my number. That is my answer of how many different ways the cello and the piano can play an order of those events. Boom. Cool. How big is this? Well, it's big, of course. We all pair up. I'm a pianist. I need a cellist with me. You know, everyone plays the piano or cello. We all pair up. We play a billion of these every second, and we still wouldn't finish, even if we had done it for the entire universe's length. So, of course, this is a big number. We won't be able to play them all, unfortunately. Though you can get a recording, or you can make a recording if you want. This is going to be one of my projects to do. I record each of the sonorities myself, and then someone, cellist, records each of the sonorities his or herself, and then you just have a computer, you push play, and it will randomly do it. And then it'll have them all there. Of course, you won't be able to listen to them all, but they'll all be there, possibly. Right? All of those down to the 645th one. That's all I'll read for that number. I won't read all that other crap. All right, heavy hitter number 2, and we have just enough time, I think, to go. Here we go. The big one. This is maybe the most famous piece of music in this whole genre of what we call indeterminate pieces. Klavierstück Elf, that just means piano piece number 11. He wrote a bunch of piano pieces. This is his 11th one. And it's this big piece of paper. It's not quite as big as this whiteboard, but it's almost as big. It's probably this big. And what it has is it has 19 little fragments of music. You know, here's a little fragment, very small. This fragment's a little bit bigger. Of course, you can see the fragments, you can see some of them. And the rules are pretty simple. Here's what you do. You randomly glance at any of those fragments. Okay, remember there's 19 of them. You randomly glance at one and you play it. And then once you are done playing your randomly glanced at fragment, you randomly glance at another one and play it. This is easy, right? And you keep doing this, rinse and repeat, until you reach a fragment that you have already played twice. Once you've played it twice, and then you look at it for the third time, you don't play it for the third time, you just look at it for the third time, and you stop, and that's the end of the piece. You know, with the rules, you have to understand the rules well if we're going to model this. They're pretty basic. Randomly look at something, keep doing that. Keep randomly looking at something until you come to one that you've already played twice. Then stop. There are other rules. We're disregarding those rules. At the end of every, I'll show you this. At the end of every fragment, it tells you what tempo to play the next one that you randomly look at, what dynamic to play it at, what articulation to play it at. And so, for you performers out there, this is really hard to play. Because you have to, at the end of something, you have to say, okay, whatever I randomly glance at next, I have to play it fast, and I have to play it really quietly. And then you randomly look, and you happen to find the hardest one. You sigh, and then you try to do it. Yeah. It's really hard. All right, so how many possible realizations are there? Anyone figured it out yet? You got it? You do the calculation in your head? Yeah, this is hard. But this is fun. First, let's argue about how to interpret the rules. If I say randomly glance at something, and then I say, now randomly glance at another one, what does another mean? Does that mean that you can glance at the same one that you were just at, or does it not? What do you think? This is a performance question. This is a, well, how do we interpret the rules, right? It's almost like a constitutional question, where how do we interpret, some of the famous phrases in our Constitution or our Bill of Rights? Well, we have two interpretations. One would be that you are not permitted to look at the one that you just played. So you randomly glance at one, and when you randomly glance at another, you may not look at that one. You have to look at one of the other 18. All right, that's one interpretation. The other interpretation would be sheer randomness. If you randomly look at one and then you do it again, it could very well be that you look at the same one. All right. One of them was already solved in '96 when I was 16 years old. And they did, they're combinatorics professors up in Waterloo, Ontario, Canada, Waterloo University. And they published this cool paper because they are mathematicians who don't know much about music, or don't know much about music at all, and found this cool piece and wrote about it. It was like, they beat me to it. Because I didn't know about this until I was really far into this research. So I was doing this during my master's. And I thought, oh wow, that's going to be cool. I'll get this published. And it's like, well, it's already done. Bummer. Turns out though that it was a little bit vindicating to know that someone else was actually doing this. Because this is kind of weird stuff. And then two, that when I got it right. It's like, vindication. That's just all that. Anyway, all right, so we can't do that one. I mean, I guess we could, but it'd be a little bit boring because it's already been done and published. So why don't we do two? Because they didn't touch two, and their method of doing one did not permit the fragment to be played twice in a row. In other words, it did not permit me to look at one, and then when I randomly look, to look back at that same one. And their methods didn't allow it. It wasn't generalized to be able to handle that. So that's how I interpret it. So that's what we're going to do. All right, we have a little more than 15 minutes. We can do this. Let's break this up. All right, this is the last one, so try to stay with me. This is the hard one, but it's the last example. We're going to break this up. We're going to break it up just like we did with our Mallarmé. The first case that we're going to look at, the easiest case, is going to be we're only going to have one fragment that we pair up. In other words, only one fragment are we going to play twice. And of course, that means that that's the fragment that we're going to randomly look at and the piece is going to end. Case 2, we're going to pair 2 fragments. Case 3, we're going to pair 3 fragments, and so on. This will make sense. And we'll get all the way to 19, and we will pair all 19. Of course, pairing all 19 is pretty interesting, because if you have all 19 that you have played twice, right? It doesn't matter which one you look at now. You've already played every single thing twice, the piece is going to be over, right? So the end is easy, the beginning is easy, the middle is wonky. All right? Our plan is going to be, we're going to count up these, and those, and those, and those, and we're going to count them all up together. We're going to have a big old number, and we're going to celebrate that we figured it out. Let's look at case 1. Remember, this is the case in which only one fragment is going to be played twice. And that's, of course, going to be the fragment that we look at. So what's the shortest way of possibly playing this piece? How long would the shortest length be in case 1? You're right, 2. I'm going to randomly look at one. I'm going to randomly look at that exact one again. And then I'm going to randomly look at that one again look at that one again for the 3rd time, and then the piece is over. Right? What would be the longest way of doing this, though? We're only allowed to pair up one fragment. So I would have all 19 fragments played, and one of them played twice. Right? So that's 20. Everybody is going to be played one time, except one of them, which will be played twice. So one guy gets 2, and all the other 18 only get 1. Okay, so every one of these realizations, we have to consider 2 things, and this is going to be the part that gets a little bit more complicated, but we'll be okay. All right. How many fragments are going to be used? How many choices do we have? And then also, how do we arrange the paired fragments? And you'll see what I mean in a second. The easiest way to do this is let's look at a table. Okay? Let's look at the easiest one that we just did, 2. I use uppercase A's and uppercase B's and uppercase C's to mean the ones that are going to be paired. And then these little X's, these just mean these are unpaired ones. Does that make sense? Just anything, any old one that we're not really caring about pairing. So let's look at this one. This is the easiest one of all, right? We play it, we're going to look at a fragment, we're going to play it, we're going to look at the same one, we're going to play it, we're going to look at it again, and it's over. So how many choices do we have for all of our fragments? Of course, we have 19. And how many different ways can we arrange this? Well, just one. To the listener, you don't know which one came first or which one came second, right? This is just going to sound like one arrangement. So 19 times 1 is 19. Let's go to this one. How many fragment choices do we have in here? Well, we have 2 fragments that we're playing, so we're 19 times 18 if we remember. Right? But then how many ways can we arrange this? I could have an unpaired fragment and then two paired. I could have the two paired like that, or I could have the two paired like that. Y'all agree? 3. So, 3. Good. If you all agree, you should be able to do this. How many fragments do we have to choose from in a length of 4? We have A, of course, and we have 2 of them that are unpaired. So 19, 18, 17. Agreed? How many different arrangements? Oh, let's try it. Why not? Quickly. What am I missing? X, X, A, X, X. Is that it? I think. Correct me if I'm wrong. Oh, I was right. All right, cool. And we multiply all that. All right, good. Let's stop doing this one-by-one stuff and let's actually, make a nice little way of looking at all of them at the same time. Do we see how I can model this pretty easily? We've done this before. Easy, right? This one, how about this? That one's a little tough. Y'all see why? Y'all see how to do this, especially you math folks? Think about what this is. I'm choosing 2 places in however long it is, right? Here's something of length 5. I'm choosing where to put 2 of my paired fragments. So it's 5, choose 2, or 4, choose 2, right? Or n, choose 2. With me? All right, so I multiply these things together, and what do I need to do all of the ones from case 1? I just have to sum. I sum that from our lengths. So from 2, length 2, which is our shortest, to length 20, which is our longest, I sum that, and I have that, and that's case 1. Now, of course, we have 19 cases to go, so either we hurry up and do case 2, case 3, case 4, or hopefully we can find a pattern, and that's what we're going to do. We're going to find a pattern. Let's do one more case, or let's look at case 2. We're going to start finding patterns in case 3. I promise, and we'll be done and out of here. This is case 2. So remember, this means 2 of our fragments are going to be paired up. So now, what's the shortest length possible of this? We have to pair up 2 of them. So the shortest length is going to be 4, right? We're going to pair up one, and pair up another somehow, and then we're going to look at one of those 2 fragments, and the piece is going to be over. What's the longest one now? Well, 2 of the fragments are going to be played twice, so that's 4. And the remaining 17 fragments are only going to be played once. So 17 plus 4 is 21. Okay? This is different. Last time, when we had AA as our paired fragment, we only had one arrangement of AA, because AA was the same as AA. If we flipped our A's around, it didn't matter. There's no way to hear the difference between that. But when I have AA and BB, when I have 2 fragments now that are being played, I can arrange this in different ways, right? I could play a fragment first, play it again, and then play the other one. Or I could play it like this, whoops, B, or I could play it like this. And I want you to know that that's all of them. Because do we see that this one, to a listener, would be exactly the same as this one? Because you don't know which one's first or whatnot. It's just going to sound to you like you played one and then you played the same one. If you could even tell that you played the same one. I'm not sure you could because it sounds like a cat. All right, cool. This is important stuff, and hopefully that didn't go over your head. All right, so there are 3. Let's move on. Let's make a table. I left only a couple blanks here. As we can see here, we had 2 fragments, and so it was 19 times 18. Here was 3 fragments, and so 17, 16. I think you got that part fine. The number of arrangements is, well, there are 3 ways of making this arranged. There are 15 ways of making this arranged, and here let me see if I can explain why. If I had 3 ways of making this one, these are my 3 possibilities. How many ways can I put an unpaired fragment, an X, in here? I could put it here, or here, or here, or here, or here. That's 5. There too. There too. You see how this would be 5 times 3? 50? Cool. So we should be able to handle this one then. Can we do this? Can we do this blank? I don't know. How many ways can we put 2 X's in here? Oh gosh. I could do like that. I could do that, in here, that, in here, that, in here, that, or that. Trust me. A little bit laughter, that's okay. This is serious stuff, but all right, so I have to model this. The 3, of course, is always the same. 5 and 15, well, I'm choosing, it's just n choose 4. Think about that, folks. I have 6, and what am I choosing? I'm choosing 4 places of 6. That's all, right? That's all, n choose 4. These are going to save our life, because when you start getting into the huge fragments, you don't want to have, when we're at 17 length here, I don't want to have to take 2 unpaired fragments and go through. It's like, I don't want to do that. Yuck. Okay? So we sum these up from 4 to 21, and we get a big number. Now we're done with case 2. Excellent. We're done with case 1. We're done with case 2. 17 more to go. No, 1 more to go, and then we'll just summarize, and we'll draw conclusions, and we'll solve it, and we'll be done. Okay? Shortest length of 3. I think you get this now. We're pairing up 3 fragments. That means 6. If I pair up 6 and then play every other fragment that we have, all 16 more, 22. Yes. Arrangements of shortest length. Oh, God. Okay, well, how about I just write them out for you? I want you to see how this works, because this is going to be important for later on. If I put a new fragment out and just make it go through like that, you see what I'm doing? The A goes like that. And then that was this. That one was this. And then that, B, C, C, B, is this. Oops, that one. Right? And so we're going to be able to figure these out too. This is just a little heads up of how we're going to figure this out later. Cool. 1 more table and then we're done. And I'm just going to give it to you. I'm not going to make you do it. Here's the table. Cool. And then what are we going to do? We're going to sum this big baby from 6 to 22, and then we're done with case 3. Boom. All right. Let's look at our patterns. Enough case-by-case study. This is exactly, by the way, I'm walking you through exactly how I came to do this. I talked to some professors at UNCG about this when I was finishing up my PhD, and they solved this thing in like it took them 20 minutes, and he had this formula that was like this most elegant, beautiful looking thing, and here I had been like crunching numbers for, so goes to show you, and there's a lot of ways to get to the right answer. Some are more genius than others. This is not genius, this is more like, blue collar. Just knock it out. All right, we have our cases. Let's stop here and see what patterns we can do. Tell me, what are these numbers again? The 2 and the 20, or the 4 and the 21, and the 6 and the 22. Remember, these are our lengths. I see a 19 factorial at the top everywhere. Whew, I can keep that. 20, 21, 22, hey, that's the same as this. This is helpful. 2, 4, 6, hey, that's the same as this. That's helpful. Do you see how we could figure out a pattern here? We certainly can. Here's the pattern. For any old case, this is the minimum length of each case. This is the maximum length of each case. 19 stays the same. This is the max length. There's the minimum length, like I said. And the only interesting thing is this base forms. Here there wasn't anything, but here there was this random 3, and here there was this random 15. Crap. Except for this, I can understand everything else. I could make a formula where everything else is, to some dummy variable, and I can solve it all out. I just need to know this, the number of base forms. It's the only thing we have left. All right? So, first of all, let's make a common variable C, and let's do everything except base forms. Minimum length. How is the minimum length related to our case? If case is 1 and the minimum length is 2, case 2, minimum length is 4, case 3, minimum length is 6, it's just 2 times, right? So 2 times the case is our minimum length. Our max length is even easier. Case 1 is 20, case 2 is 21, case 3 is 22, just 19 plus C. And base forms, how do you relate 1, 1, 2, 3, 3, 15, 4, you see a pattern here? I didn't. This one stumped me for a while, so I had to get my pen and paper out. And I had to figure out how these numbers actually work. So first of all, when I looked at case 1, of course there was only one way of arranging it, like this. When I looked at case 2, I found that there were 3 ways of arranging it, right? A, A, B, B, A, B, A, B, A, B, B, A. So I went from 1, then I went to 2, I saw how that worked. Ah, I see how that worked. I took my old form and just made an A go through it. There, there, or there. See? Ah, my next one, I can do exactly the same thing. This is what we talked about before. Make my A go through it. My A go through it. Aha! So instead of looking at this as 15, why don't I look at this as 1 times 3, 1 times 3 times 5. Now I see the pattern here. It was easy all along. It's just odd numbers multiplied by each other. And I, of course, like an idiot, or like a good, true blue collar, I did case 4 and I did case 5 all on the board, so I had just board of this. And I made sure I counted, and it was right. It does work this way, after all, and this is just a fancy way of saying odd numbers multiplied together. Got with me? This is just regular old odd numbers. All right, we're to the end. You made it. Let's substitute all of our findings and use C. Instead, my max length now, my minimum length is that. My base forms is this crazy thing. My max length was that. My minimum length was that. And then sum this from 1 to 19. Of course. Done. That's it. That number. Exactly that number. It's about 2.5 times bigger than the number for the 2 bozos up in Waterloo that already solved it. Not bozos, I love them. Solved it before I did. And that makes sense, right? Because they did not allow you to look at a fragment back to back. So of course it's going to be a smaller number, right? It's about 2.5 times. How big is this? I said this to my theory class already, so they've heard this. This number is almost exactly this big. Let's say you had this many drops of water from an eyedropper. Okay? Take your water in your eyedropper and start filling up the ocean. Okay? You can fill up the ocean with the eyedropper, but not just once, or twice, or 3 times, but you can fill up the ocean as many times as there are drops of water in the ocean. So, it's a lot of oceans. A lot of water. Which is why we have water. Okay, so the $1 million question of the hour, or the some no-million question of the hour. Why? What? What is the point of this nonsense? All right, well, I went on and on and on and on and on when I was writing this, talking about why to do this. To summarize in 2 seconds, I don't know, doesn't it help to know in any artwork, doesn't it help to understand the universe in which it lives? Yeah. If this piece can be played this many ways, or this many ways, or this many ways, you know, I feel like this helps me understand the work if I understand its entire universe. And from that entire universe, I can, yes, I'm only going to play a sliver, maybe, in my lifetime of what it has to offer. And that gives me even more respect for it. I don't know if I sold you on my why. It certainly sells me, because I feel very attached to these pieces now that I know this is how big they really are. They're not just this little piece of paper, you know? It's not just a little book with 5 stories in it. It's more drops of water than there are in the ocean. You know, it's like, they're huge, even though they were so small and